Today's my topic is a theoretical study of the emergence of periodic solution for the inhibitory NNLIF, nonlinear leaky integrating fire neurons models with synaptic delays. So maybe in the last the question and chose talk, he speak about the inhibitory network and maybe periodic motion with the Gaussian shape. It is associated with my talk. And maybe you remember the 2 days ago, some talk, the Dr. Alejandra Ramos Roja, he is also associated with my research. Okay, anyway, my collaborator is Pierre. He's now is in Oxford. He was a student of the Sorbonne University in Paris. And Salot and Smet is also my collaborator in Sorbonne University. Okay, let's get started. Okay, first of all, I want to introduce my contents in this talk. During my talk, I show you the 4 different equations. The first and the second equation was proposed in the previous work in the 1999, the Brunel and Hakim's articles. And these equations have been introduced in the Alejandra's talk. It is completely same. On the other hand, the third and the fourth equation are our proposal equations, which has the form of delay differential equations, stand for the DDE. Okay. Okay. Now I explain the relation between these equations. Okay. Okay. And the first one is called LIF model. It is a microscopic model which describes the dynamics of many neurons. And from this microscopic model, we can derive the Hooker-Planck equation, which is the second equation, this one. Okay, this derivation is already studied in the Brunel's articles. This is the previous result. In my research, we have some delay differential equation. The third equation comes from this Hooker-Planck equation. This is our first result. The last equation, this one, is completely consistent with this fourth equation under some change of variables. Okay, this equation is completely the same. Okay, let's get started. This is the background in my research. Please remember the some term gamma oscillation in hippocampus. Maybe everybody knows the hippocampus is important for humans because it is associated with memory. Gamma oscillation is a kind of brain waves. Maybe you know alpha wave and beta wave, but they're the same. Okay, but the typical property is the high frequency in gamma oscillation. Some research says to us the frequency is around 26 to 70 hertz. This is a high frequency, rather compared with the alpha wave and the beta wave. Okay, in this research, they show some experimental result. They observe the gamma oscillation, like in this figure. Okay, this is a power spectrum in brain of mouse. Okay, in the subfield called CA3 of the hippocampus has this typical oscillation. The peak attained around 40 hertz. This is called gamma oscillation. Okay, this gamma oscillation result in the group dynamics of neurons. Okay, maybe many mathematicians imagine group dynamics of many neurons comes from the complete synchronization. Maybe you remember the Kuramoto synchronization. But in this phenomena, the situation is a little bit different. Okay, let's see this right figure. This is probability of firing rate of each neurons. Okay, 40 hertz means neuron should fire per 25 milliseconds. Okay, but this figure shows us there's not complete oscillation because there's a lot of variation of the timing, firing timing. Okay, maybe this is a kind of contradiction. So here's the question: is this phenomenon can be realized by some mathematical model? Okay, this is a mathematical question. To answer this problem, Brunner and Hagen proposed some NNLIF model and derived a Hooker-Planck equations shown here. Okay, this equation is completely the same as in the Alejandro's talk. Okay, the completely same, but we consider the inhibitory network. Okay, the previous speaker Charles considered excitably network. And maybe I think Alejandro also considered the excitatory network, I think. But in this talk, we focus on the inhibitory network only, okay? Okay, let's see this movie. This is a numerical result of Hooker-Planck equation, okay? This movie is now goes, okay? The time proceed, but the pattern stopped. Okay, this means that our Hooker-Planck equation has a stable stationary solution. In this case, we assume that B is equal to -10. Okay, the next movie, we set B is equal to -300. What happened? Maybe you know, some periodic motion occurs. Okay, from the mathematical viewpoint, this is a kind of bifurcation, maybe, you know, Hopf bifurcation. So this phenomena can be characterized by the destabilization of the stationary solution. And maybe we can get the periodic motion. And the point is the spatial profile. Spatial means the variable V, okay? In this talk, I called variable V a spatial variable. And the spatial variable is almost a pulse, okay? So this is a periodic motion of pulse. So today's our goal is to characterize this periodic motion of pulse in Hooker-Planck equation, okay? Okay, here's our, I want to show you our strategy in my research, okay? Please remember the previous movie. Some pulse keep its shape and move translatory, okay? So we assume the function law can be approximated by some spatial profile phi with some moving coordinate v minus ct, okay? This is a strong assumption in my research. Okay, so how can we determine the phi and c? Okay. Let's see this Hooker-Planck equation again. I substitute this function into this equation. We also assume that the right-hand side is close to 0 because some pulse has a tail, and this terms determined by this one, and this term at the VF is small because this value can be determined at the tail, okay? Tail has a small value. So this is close to 0, maybe. Oh, sorry. And okay, we substitute this one into this one, okay? This term comes from this one, okay? And this term comes from here, okay? Please differentiate this one minus 5, okay? It is very easy. And this one has from this one, and the final term comes from the diffusive term, okay? Here, focus on these three terms, okay? We correct 3 terms, we have this differential equation. This equation has a special solution, Gaussian. You know, this has the pulse shape and the symmetry pulse, okay? So we can determine the function phi. Next, we focus on the red one, okay? Let's see. Here is the first derivative of phi, and also here's a first derivative of phi, okay? We kick out these values and we correct the remainder term. We have this one. This is the scalar equation for function C and with time delay. This is called DDE. And the nonlinear term are given by this one because the Gaussian function can be explicitly determined by this one, and the NT can be determined by this one, okay? So this is our DDEs. Okay, maybe you're familiar with DDE. So this is a classical form of typical DDE. So maybe we can easily expect it that this equation has a periodic solution via Hopf bifurcation. It is true. We can verify this theorem rigorously. This is our first result. Okay, we assume this condition. The time delay should be large. Then there is some periodic solution C satisfying these conditions. Okay, here C0 is independent of time delay D. This is a natural technical condition. So I want to say something for this condition. This condition can be satisfied under the case that D is negatively large, okay? Inhibitory network, okay? Okay, let's see this figure. This is the comparison between the numerical result in Hopf bifurcation and the DD. Red line is the Hopf-Planck equation, and the blue one is the DDE. Unfortunately, the minimum value here is a little bit different, but other things is a consistent, right? Period is okay, and the profile in the low region is okay. So I want to say that DDE is a good approximation of Hopf-Planck equation. I think this is good for us, but here is the technical difficulties. In this theorem, we assume that D should be large. Okay, the next question is, what happens when we fix D and D is negatively large? Okay. I want to show you the second numerical result. Okay. This is a result for the DDE. Okay. Periodic solution. Also, this is a periodic solution. But the B is different. Okay. And in the left figure, B is assumed to be minus 1,000. In the right figure, we assume that B is minus 10 to the power 6. Okay, please compare. The first one is a value. Okay. Minimum value or maximum value, okay, which is okay. Anyway, the value is completely different, okay? This minimum value is very, very large than this one. Next one is the period. A little bit, this length is larger than this one. From this numerical result, we expect that there exists a periodic solution C in DDE satisfying these conditions. The value tends to minus infinity and the period goes to infinity. From this expectation, we do some rescaling in DDE. Unfortunately, I don't have much time to explain it, but anyway, I want to introduce this scaling. Please remember, B is close to minus infinity, so beta is close to 0. And the new function U is explicitly given by this one. Here is the original function C, okay? We using this function, then we can get another DDE named P for function U, okay? What happens in P? We do numerical simulation for P. We have this special periodic solution. Let's see. This is the graph of function U, and the value is 0.5. Okay. If we change beta, the smaller and the smaller, the graph is almost do not change. Okay. So I mean, if beta is goes to 0, then the function u converges to some saw-shaped periodic solution. This saw-shaped periodic solution characterized by two properties. One is linear line here, okay? Another thing is discontinuous point around here, okay? This is a simple characterization, okay? Our final goal is to find a saw-shaped periodic solution in P. And please remember, P is completely consistent with original DDE under this change of variables, okay? So I do not have much time to explain it, but anyway, we have some formal solution like this one. This is not a rigorous proof. There's only formal approximation. Okay, the function u can be approximated, the function u0 and phi. U0 is called outer solution. On the other hand, phi is called inner solution. These terminology are used in the singular perturbation method, okay? U0 can be given by this one. This is a linear line, okay? Because U0 should satisfy this differential equation, okay? This equation easily obtained because, okay, let's see, this is the first term. Beta is close to 0 and the U is a positive. So we kick out this one because this is close to 0. Also, the second term is close to 0, okay? Okay, this one is a positive, but this one is a champion because minus exponential 2 over beta, okay? U is a positive. So this is close to 0. So we have this differential equation, okay, naturally. So we have this function. On the other hand, inner solution, to get inner solution, there's some complicated calculation, but anyway, phi can be given by this one. Okay, how about the approximation? Okay, please let's see this figure. Okay, red line is the numerical result of P, and the black line is associated with the formal solution. This one. Okay, it's completely consistent, I think. Okay, the right figure is expansion around here. This is a continuous point. Okay, black line is the formal solution of function phi, and red line is the numerical solution of the P. Okay, it's a consistent, right? Okay, you agree? Okay, so I want to say our numerical solutions can be approximated by the formal solution. And interestingly, we can determine the period by this one, okay? Because our formal solution can be explicitly. Okay, this is my conclusion. In my talk, I want to characterize the periodic motion of plus in Fokker-Planck equation. Our strategy is as follows. The function rho can be characterized the spatial profile phi and the function c. Okay, C satisfies this DDE, so we have the periodic solution. Finally, we have a formal solution. By using it, we can get a special form like this one. The function u is a source shape, so we can get many information from this one. Okay, I want to stop here. Thank you for your kind attention. Thank you very much.
Thank you very much. Are there a question in the room?
Hi. So
Hi.
I think I got lost a little bit. The starting point, at some point you introduced a DDE for C of t. And
Okay.
the bit where you lost me is you make a change of coordinates and you now write down an evolution, some equation in U. And I'm
U.
trying to understand whether the new dynamical system for U that you then analyze with inner and outer solution is delayed or not. Because, it is delayed by beta, so I see it only now. Sorry.
Yeah. You're right. It is a very good point. Okay. In the formal solution, there's no effect of delay, but here is right? In the differential equation, there's no delay, but this is the delay effect.
Okay, so the way I understand this is that the moment you look at things in U, your evolution equation is no longer delayed, but the outer and inner solutions you can construct with, with a delay information in there.
Yes.
Yeah.
Yeah, that's
Okay.
right. That's right. That's right.
Thank you.
Okay, Olivier has a question.
Yes, thank you for your presentation. I got lost a little bit as well. In the first method, where you use the delayed differential equation,
Yes.
do you have a mean of comparing the solution to this equation to the solution of your equation analytically? I mean,
Analytically, it is a very difficult.
Uh-huh.
Sorry, it's an ongoing project, but very difficult.
Very
Yes.
difficult. Okay, thank you.
Very difficult. Yes.
Thank you, Olivier. I take time for one more question. It's clear that you rescale everything to have VF, VR, and so. Can you tell us the order of B in order to obtain oscillation with biological quantities? I mean, values of your parameter which are biologically plausible.
Sorry.
What is the value of B if you take VF and VR as the membrane potential?
In the original equation, this one? In this one?
Yes.
Parameter B?
What is the typical value of B in order to observe oscillation? I mean, B goes to infinity is maybe not adapted to the biology, but you observe oscillation for large B.
So this means the effect of the inhibitory network, the effect of inhibitory. The strong connectivity of the inhibitory neurons. B means like that.
Okay, thank you.
But, excuse me?
Yes.
Related to that, if B is going to minus infinity, then there should be oscillations, then still, in the end, they should be stopped.
Stop?
Isn't that so?
Yeah,
if B is very, very small, it's going to minus infinity.
Yes. In our model, the pulse can move, even if the B is negatively large.
So you expect that the oscillations pertain for any negative value of B?
Not to any. The real B should be negatively large a little bit, because let's see.
A little bit means if a little bit. So the question is there another bifurcation?
Okay. In the Hooker-Perk equation, we never know. But in DDE and our new P, there's no bifurcation as far as we know. No bifurcation. Only one Hopper bifurcation.
Okay, thank you.
Yeah, no secondary bifurcation. Yeah.
Other questions? Okay, so thank you again.